Networks, Computer Networks. This is Parvathi, Assistant Professor, Department of CSIT, MLR Institute of Technology. In today's session, we are going to discussing about error control in data link layer. First, let us see the overview of today's session, error detection technique. In previous session, we already discussed about error detection techniques. There are the 4 different error detection techniques are there. Those are the VRC, vertical redundancy check, longitudinal redundancy check, checksum, and CRC, cyclic redundancy check. In previous session, we already discussed about VRC, that is vertical redundancy check, and also we discussed LRC, longitudinal redundancy check. These 2 topics we discussed already. Today we are going to discussing about what is checksum, how to detect the errors using the checksum, and also we discuss about CRC, that is cyclic redundancy check. First, let us see what is checksum, how to detect the error using the checksum. So, checksum is nothing but check plus sum. First, we have to check with the original data and we have to do the sum, that is the checksum. So, in this, sender side and receiver side is there. Sender side, receiver side means this is the sender, this is the receiver. How the error detection is going to be happen between the sender and receiver only, right? When the data is sending from the sender to the receiver, then that time only the error is going to be happen. That is, sender side is there, receiver side is there. That is, sender side as well as the receiver side. In the sender side, we have to do the checksum creation, and the receiver side, we have to do the checksum validation. Means, sender side, we have to do the original data along with the redundancy bits. At the same time, here receiver will validate the exact I received the data or not. It will check whether the data is correct or not. That is the receiver side. There are 2 processing methods, that is the sender side method as well as the receiver side method. So, sender generate the checksum. First, sender, whatever sender is there, he will generate the checksum and sends the original data along with the checksum. So, original data along with the checksum, sender will send to the receiver. That is the checksum. Checksum creation is going to be happened in the sender side. And coming to the receiver side, receiver also having the checksum. Here also, receiver is also doing the checksum. Checksum also generate the checksum from the received data. Whatever data is received from the sender, based on that, it will generate the checksum. That is the receiver side. If the generated checksum, if these generated checksum is at the receiver side, all are zeros. Means whatever sum is there, if all are zeros came, finally all zeros are there, then the data is going to be accepted. That is the main concept in checksum. Means whatever receiver received data using from the sender, so after doing the checksum, if he will get all zeros, then the data is going to be accepted. That is the checksum. So how the sender follows the steps? First, see here. First, the data is divided into k sections. Whatever data is going to be there, this is the data. It is going to be divided into k sections. This is the sections or blocks. Those are those having the number of bits. Means each section is having some number of bits. So, here is some number of bits, here is some number of bits. Here the data is going to be divided. All sections, whatever sections are there, these are different sections, right? All sections are added using the ones complement. So, using ones complement, we have to add these 2 data. These 2 data like this, we have to add the all sections. The final sum, whatever getting after adding all these data, the final sum is the bitwise complemented. After final sum, we have to do the complement. Bitwise complement we have to do. Means if ones are come, we have to add to 0. If zeros are come, we have to add to 1 to get the checksum. That is the checksum operation. From the original data, we have to add the checksum, right? How we are getting the original data like this. The sender sends that original data along with the checksum to the receiver. These are the steps the sender is followed. So, next, how the receiver receives the data here. See, the data. Again, the receiver will receive the data into the same number of k sections. It is going to be divided. Each section is having number of bits. And all the sections are going to be added. So, whatever receiver received, all sections each are going to be added. Each are going to be added using the ones complement. How we are doing it the sender side. Same way here also doing the data plus checksum. And then the final sum. Whatever final sum we get, right? That final sum is a bitwise complement. We have to do the bitwise complement. Again we have to do the complement here. Means ones are going to be converted to 0. Zeros are going to be converted once. If the result after doing the complement, if the result all are zeros, all came as a zeros. If all are zeros, then the data is going to be accepted. Then otherwise it is going to be rejected. If all zeros came, then only it is going to be accepted. It is going to be accepted. That is the receiver side process. See, all these steps we will see with one example. Here is the example. So this is the original data. So this is the original data. This data is going to be divided into 4 sections. We are dividing this total data into 4 sections, and each section is having how many bits? 8 bits. This is the one section. This is the 1, 2, second section, third and fourth one. We are dividing each and every data into section wise. The data is having the number of bits. So each section is having how many bits here? See, 1, 2, 3, 4, 5, 6, 7, 8. Each section is having 8 bits. Like that we are dividing into 4 sections. 4 sections we are divided. So there are 32 bits are there. Total how many bits are? 32 bits. We will divide these 32 bits into 8 bits, 4 groups. We have to divide it into 4 sections or groups, or it is going to divide each bit, each block is having how many? Total n bits, that is the 8 bits. So how the sender side the data is going to be sent? See, take any 2 blocks. So total how many blocks are there here? Total 4 blocks are there, right? Take any 2 blocks of the data. We have to do the ones complement operation here. Ones complement arithmetic we have to do. And next, after doing the ones complement, next take the next block. After adding these two, we have to go for the, after completion of these two sum, next we have to go for these two. The result of this with this one, we have to do the sum. Next block of the data, add to the result of the last addition. Addition of these two at the same day along with this one we have to check. So perform the addition until the blocks are going to be added. Till this block we have to do the addition. Afterwards, take one's complement of last sum obtained. Whatever last result came, right? From that we have to do the ones complement, and it is the checksum. Whatever last we get the result, right? That is the checksum. Transmit the original bits along with the checksum to the receiver side. So how it is going to be sent? See here, this is the original data. See, whatever data we said here, that is only I am considered here. This is the original data. So I am considered this is A, this is B, this is C, this is D. These are the 4 sections. And each section is having the 8 bits. Here is 8, here is 8, here is 8, here is 8. 8 bits are there. So first I am doing the addition of A plus B. First I am doing A plus B. See here, 1 0, 1 1, 0 0, 1 1. And next 1 0, 1 0, 1 0, 1 1. This is the B. I am doing the sum. How we have to do the sum? Already in digital algebra, how we are doing binary sum already we know, right? Binary sum, how we have to do? Like if the 1 0 is there, it is 1 only. If it is 0 1 is there, that is 1. And if it is 1 1 is there, if it is 1 1 is there, that is 0. 1 is going to be carry. Carry is 1. And next, if it is 3 ones are there, it is going to be 1. Again 1 is going to be carry. Like this we have to do the addition, right? So here, first see here 1 1. 2 ones are there means what we have to get? 0. And 1 is going to be carry here. And next, how many ones are there? Total 3 ones are there. 3 ones means what? We have to do the 1, and next 1 is going to be carry. 1 is going to be carry here. And next 1. Here is only 1 1. Here is 1 only. And next here is 0. 0 and 1 means only 1. And next 1 0 means 1 only. 1 1. Again 1 1 means what? 0. Here is 0. Again 1 is going to be carry here. And next here is 1. 1 is here. 1 1 means 0. And 1 is going to be carry here. That one is this one. And again carry 1 we have to add with this result. This carry 1 we are adding here. See, here is 0 1 1 again remaining as it is. And here A plus B result is completed. This is the A plus B. And next we have to sum with the C. We have to do the addition with the C. C is nothing but 0 1 0 1 1 0 1 0, that is the C. So same way we have to do the addition, binary addition, that is 1 0 means 1 only, 1 1 means 0, carry is going to be added, 1 1 means 0, again carry is going to be added, 1 1 1, 3 ones are there means 1, again carry is going to be added, again 3 ones are there means 1 is going to be added and carry is going to be there. And so 1 0 0 means here is 1 only, 1 1 means 0 only, and next here the data carry 1. Next 1 is going to be here. There is no carry. Means there is only 1 is there. And next for these A plus B plus C, again we are going to add the D. We have to do with the addition D. So here again 1 means 0. 1 is going to be carry. Based on these only I am doing. Based on these conditions only I am doing. So 1 means 0, only 1. Next only 1. Next 1 0 1 only. 1 means 0. 1 is going to be carry. 1 is 0. Again 1 is going to be carry. 1 is 0. Again 1 is going to be carry. 1 2 3. 3 ones are there means 1. And next 1 is going to be carry. This is the 1. And next this one again we have to add to this particular result. So here is 0 1 means 1 only. Remaining as it is 1 1 1 0 0 0, like this it is going to be added. So this is the final result. This is for A plus B plus C plus D. After doing all the sum, what we have to do? We have to do the 1's complement. 1's complement means what? 1 is going to be converted to 0. 0 is going to be converted to 1. That is nothing but the 1's complement. So 1 is going to be converted to 0. 0 is going to be converted to 1. Like this we have to do the sum. This is the checksum of the sender side. Along with the original data, along with these original data, we have to add this checksum data. That is the sender side. See this picture here. Total here is transmitted bits from the sender. See, first 101, 10011. This is the first one. A, B, C, D. So checksum I am going to add to the original data. This is the checksum of the sender side. 011, 0000. That is going to be added to the original data. This data I am going to the sender, from the sender to the receiver. This is the sender side process. Now you can go for the steps once you can understand easily. First we have to divide into 2 blocks, means we have to perform the addition of 2 blocks using the 1's complement arithmetic, means binary addition, and adding the next block to the data with the result of the last addition. And next perform the addition of the whatever until all blocks is going to be completed. We have to do the addition. And finally we have to do the 1's complement of the data. Means 1 is going to be converted to 0, 0 is going to be converted. That is the 1's complement and it is the checksum. And transmit that original data to the checksum of the receiver side. This is the process of the sender side. And next we have to see for the checksum operation at the receiver side. How the receiver receives the data. Take any 2 blocks of data. Same how we done in the previously for the sender. We have to do the addition at the receiver side also. So take the next block of the data and addition of the result of the last addition and perform the addition until all blocks are going to be added. And again we have to do the 1's complement, last sum update, and if the complement get the all zeros, we have to check only this condition. If all gets all zeros only, then the data is going to be accepted. Otherwise the data is going to be rejected. See, this is the data we received from the receiver. First we are doing the addition of these two, same what we did last time, right? In the sender side, like that only we have to do. 1 1 is 0, 1 if the 1 0 is there, 1 0 1 is there, 1. Next one is what? If the 1 1 is there, it comes to 0 and carry 1 carry is going to be there, carry is 1. And next if 3 1s are going to be there, that is 1, and again carry 1 is going to be there. That is the condition for doing the sum. So here 1 0 is 1, like this we are doing the same here. Till here same only. A plus B plus C plus D already we did previously, and whatever checksum that we added, D plus C we have to check. This is the D, right? This is the D. A plus B plus C plus D. Till here A plus B plus C plus D. And next we are adding D to E to this particular data. So here we have to check this condition. 1 0 means 1 only. 1 0 1, 1 0 1, 1 0 1, 0 1 1, 0 1 1, 0 1 1, 1 0 1, means all ones came. So what we have to do after adding all the bits, we have to do the 1's complement, right? We have to do the 1's complement here. 1's complement means 1 is going to be converted to 0, 0 is going to be converted to 1. So like this, if we do the 1's complement, we will get all the zeros. If we get all the zeros, what? The data is going to be accepted, means there is no errors in that original data. That is the receiver side. Like this, the receiver will accept the data. This is the concept in the checksum. The final result is all zeros, means the received data is the correct at the receiver side. So how the performance is going to be there in checksum? The checksum will detect all the errors involving odd number of bits also. Previously it will not solve by the VRC and LRC. That is going to be solved by the checksum. And it detects most of errors involving an even number of bits also it will solve. The most disadvantage here in this checksum is if one or more bits of a segment, one or more bits are going to be means in a particular section more bits are going to be damaged, the corresponding bit or bits of opposite value in a second segment also going to be damaged. Means in the first section also damaged, corresponding bits also going to be damaged, then the sum of those columns will not change and the receiver will not detect the errors. That is the main disadvantage of the checksum. And coming to last error detection technique is the CRC, cyclic redundancy check. How we are going to do the error detection using the CRC, we will check now. So cyclic redundancy check, it is based on the binary division. Based on the binary division only we are doing the CRC. So the sender and the receiver both can agree upon the generated polynomial. In maths we will see, right, in maths we discussed about polynomial equations. Polynomial equations are there. What is polynomial equation? Like this, x cube, x power 4 plus x cube, x square plus x plus 1. These types we call as a polynomial equation. Based on that it is going to be work. This polynomial can be any polynomial expression. That can be any type, any polynomial equation. So mainly it is for helping the finding the CRC generator. Why it is going to be help? Why we are using polynomial equation? For finding the CRC generator, we are going to use the polynomial equation. So these CRC bits means having the same number of bits in the CRC generator. These are going to be sender side. These are going to be generated at what side? Sender side, by dividing the bit sequence by the data using the CRC generator. So before going to the CRC generator, means whatever data is going to be there at original data, for that original data we have to add the n-1 bits from the CRC generator, whatever we get from the CRC generator. Suppose take one example here. This is the CRC generator. We are applying CRC generator for this polynomial equation. Here the polynomial equation originally is, that is, x cube plus x square plus 1. This is the polynomial equation. How we are going to write this one? 1 into x cube plus 1 into x square plus here 1 is going, x power 1 is going to be missed. That's why we are writing 0 into x power 1 plus 1. This is the polynomial equation. From this, how we will get the generator? How we have to write the CRC generator? This is the 1 from here. This is the 1. This is 1. This is 1. 1, 1. Here is 0 and here is 1. Like this, we have to generate the CRC generator. So using this CRC generator, total how many bits are there in this CRC generator? 4 bits are there. These 4 bits. So here when we have to do the original data with the n-1 bits, means we have to append how many bits to the original data? n-1. For total n equal to 4 bits are there. So n-1 means 3 bits. 3 bits of what? 3 bits of zeros we have to add to the original data. 3 bits of zeros means 3 zeros we have to add to original data. That's why we are going to use the CRC generator. And the sender will then append the data with the CRC bit and send it to the receiver. See, this is already discussed. Like this, we have to generate the CRC generator 1101 we generate. At the receiver end, what will happen? The receiver bits are divided again into the CRC generator. If the remainder is of the division of all zeros, after all, if the receiver will, the remainder of all we get the 0, then the data is going to be accepted at the receiver side. Receiver side, the remainder what will? That is the 0. Then only it is going to be accepted. See this example, you can understand easily. So the original data is 100100. This is the original data. The polynomial in the previous already we discussed, here is 1101. That is the polynomial. So 1101, 4 bits came. We have to append the original data with the n-1 number of zeros. Means this is the original data. For this original data, we have to add how many zeros? n-1 number of zeros from the CRC generator. That is the CRC generator means how many number of bits? 4. 4 minus 1 is what? 3. 3 bits, 3 zeros, we have to append with the 3 zeros. So we have to add with the 3 zeros. That is nothing but the CRC generator. So now while dividing, we will perform the XOR operation. So we are dividing, we are using the division, right? We have to do the division concept here. For division, whenever we are doing the division, that time we have to perform the XOR operation. Means in digital logic design we have like AND gate, OR gate, NAND gate, like that, right? There we are having the XOR operation, right? Based on XOR operation, we have to perform the CRC. See here, this division will be performed both at the sender side as well as the receiver side. So this is the original data. For that original data, we are going to adding exactly how many bits? 3 bits. How it is going to be decided? Based on the CRC generator. CRC generator total having the 4 bits. 4 bits means n minus 1 we have to do. N minus 1 means 3. 3 means 3 number of bits. How many are there? N minus 1 number of zeros we have to add. Means 3 zeros we have added to the original data. So the divisor is what? What is the CRC generator is there? That is the divisor. This is the divisor. This is the dividend. We have to do the division using the XOR operation. That is the condition. For the receiver side, the divisor would the same. The dividend would be the original data. So dividend is the original data and the divisor would be the what? CRC generator. Along with the CRC bits, we have to do the division. If the remainder at the receiver side is 0, then the data is going to be accepted. That is the condition. See how the division we have to do. See here. See first what is the data here? The data is 100, 100. We have to do we added 3 zeros, right? This is the sender side and receiver side. So see here I am writing divisor is this one and next is what? 100, 100, 100 and we have to add 3 zeros. These are the 3 zeros we are going to add it. So how we are doing the division? Suppose if I want to add, if I want to add the 27, if I want to divide with the 3, how we are doing? 3 9s are 27. Like that we are doing, right? Same way we are also doing with this XOR operation. XOR operation means what? What is XOR operation performs here? If 1 1 is there, if 0 0 0 1 1 0 1 1 like this is there, right? If 0 is there, we have to append with the 0. If it is 0 1, if this is 1, if it is 1 0, that is 1. If it is 1 1, that is going to be 0. This is the XOR condition. Based on that, we are performing this. So how we are doing like this means 1 1 0 1 into 1 means what? 1 1 0 1. Like that we have to do. So here we are writing the divisor, dividend. We are writing the quotient here. Suppose this is the divisor, dividend. This is the quotient, right? Quotient. So based on that we will see. So first 1 1 0 1 1 what? 1 1 0 1 only. So here we are performing XOR operation. If 2 1s are there, that is 0. If 1 0 1 0 1 1 0 0 means 0. If it is 1 1 means what? 0. 0 0 means 0. 0 1 means 1. 1 1 means 0. Like this we have to do. Again this one is going to be side. Next we have to do one more, that is 0. Next again 1 means 1 1 0 1 into 1 what? 1 1 0 1 only. See next here is 0 1 means 1, 0 0 0 0 1 1 1 1 means 0. This is going to be side. And next we are going to next 1 0 1 0. And next means what? 1 1 0 1 into 1 means what? 1 1 0 1. So here 0 1 means 1, 1 0 means 1, 0 1 means 1, 1 1 means 0. This is going to be side. And next see here, next 0, this is the 0. And next 1 1 0 1 into 1 means what? 1 1 0 1. So 1 0 1 1 1 0 1 1 1 0 1 1 0. These two are going to be side. Next one. Next we are considering 0. So here how many bits are there? Total 4 bits. Here is only 3 bits. That's why we are going to down in 1 1 0. So that time if we get 2 at the same time, what we are doing here? We have to add extra 0. So here again what we have to do? 1 1 0 1 into 1 means what? 1 1 0 1. So 0 1 1 0 0 0 1 1 0 1 1 0. So How many bits we have to consider from this n minus 1 means what? 4 minus 1 equal to what? 3. 3 bits we have to consider. 3. 1, 2, 3. 3 bits we have to take as a CRC. These are the CRC bits. This is about the sender side. The transmitted bits from the sender is original message. This is the original message along with the CRC bits. So, in place of these 3, along with 3 RCB, what we have to add? 0, 0, 1 we have to add. That is nothing but the 1, 0, 0, 1, 0, 0, 0, 0, 1. That is going to be sent from the sender to the receiver. So, again from the receiver side, we have to do the same as it is as the XOR operation from the receiver side also. Same how we did the sender side, like same we have to do the receiver side also. Same if we do like this, no? After finally, if we get all zeros, then only the data is going to be accepted. That is the receiver side. See, in the receiver side also, suppose here I am drawing. Here I am drawing 1, 1, 0, 1. Next is what? 1, 0, 0, 1, 0, 0, 0, 0, 1. This is the receiver side data. So, I am doing here 1, 1, 1, 0, 1, 1. 1, 1, 0, 1, 1 is 0, 1, 0, 0 is 0, 0, 1, 1. 1, 1 is 0. Again, next 0, 0, 1, 1, 0, 1. This is the 1. Next 1, 0, 0. Sorry, here is 1. Here is 0. Again, next is 1, 0. Next 1, 1, 1, 0, 1. Next 1, 1, 1, 0. Next is this one. Next 0, 1, 1, 1, 0, 1. Next 1, 1, 0, 0. Next, if we append this one 0. And if we append this one, if we did same time, we are getting 1, 0. Here is 1, that is 1, 1, 0, 1. So finally we received all zeros. So the receiver data is going to be accepted. If we get the result is all zeros, then only whatever sender is sended, the data only receiver is received. Means the receiver is going to be accept the data. That is the receiver side. Based on the XOR operation only, we are performing the sender side and receiver side operations in the CRC generator. So, in summary, coming to the summary, in error detection techniques, we discussed what is checksum, total how many are there, total 4 number of error detection techniques are there, VRC, vertical redundancy check, longitudinal redundancy check, and in today's session, we discussed what is checksum, and next we discussed what is CRC, cyclic redundancy check. Based on these two, how we are going to detect the error, that we discussed in today's session. Thank you.